Hi everyone, welcome to Home Learning Lab. In this video, we are going to solve best time to buy and sell stock 4. Now this is the fourth problem in the best time to buy and sell stock series of problems. I have attached the links to the solutions for the first 3 versions in the description of this video. I would highly recommend people to watch the first 3 versions first and then come back and continue watching this solution. Without any further ado, let's begin. So the problem says that you are given an array prices where prices of I is the price of a given stock on the ith day. This is very standard, present in all the versions of the problem. But there is an integer k. And what is the integer k? Integer k basically signifies the total number of transactions, at most the total number of transactions that we can do. So find the maximum profit you can achieve. You may complete at most k transactions, that is, you may buy at most k times and sell at most k times. And of course, they have added that disclaimer that you cannot do multiple buys. You cannot do multiple transactions simultaneously. You have to sell before you buy. So it has to be like buy, sell, buy, sell. It cannot be 2 buys or 2 sells, of course. And they have given 2 examples here to drive home the idea that you don't have to always do k number of transactions. That is a point where most candidates get confused. So k has been given to us as the at most number of transactions that we are allowed to do. We don't have to do exactly k transactions. So for example, in this example, k is 2, but we only have 3 prices. So you can just do 1 transaction and get the most optimal profit. That is completely allowed. But similarly here, we have k as 2 and prices array is given. And here 2 transactions are being done. That's the point that they're trying to drive home. Now, let me just copy this example real quick and I'll come to the approach. So we have 326, 503 and k as 2. Let me just write that. Let me take green color. So we have 3, 2, 6, 5, 0, 3 as the array. K is 2. Now, usually when there are problems wherein there is different profit for different actions, we cannot use greedy method. So greedy method is usually applicable when regardless of what transaction you are doing, what action you are taking, you are getting the same profit. Like let's say there is some problem wherein you have to, they are saying something like you throw a ball and you get 2 points and it's 2 points across all the actions. Then maybe you can think in greedy terms. Usually, I'm talking about usual patterns. But whenever there is a difference in profit based on difference in actions, usually DP is the way to go. What I mean by that is, in this case, they did a transaction here, got a profit of 4, and they did a transaction here and got a profit of 3. These are differing profits. So when there are differing profits, we have to take into account state relations. Like we have to take into account where did I do the previous transaction, because based on that I can do the current transaction. If I did a buy in some previous transaction in some previous index, depending on that I can take a call whether I should sell here or what should I do. So there is a state dependency here that directly points to DP approach. More specifically, since we have k number of transactions, we have to break down the problem into smaller chunks and build our solution, which is the classic top-down DP approach. Once we figure out this much, that there are differing profits involved and there are state relations involved as well, what I do right now depends on what I did earlier, and it is the DP approach, more specifically top-down DP. We have to break the problem into chunks and solve it. The problem will start solving itself. How? Here, what are the variables involved? Let me denote the variables in blue color. Let me take blue. So the first variable we will have is n. N represents the total number of elements that we have. The next variable that we have, that they have given in the problem, is k. K represents the total number of transactions that I am allowed to do. Now, there will be another variable as well, which is whether I'm going to do a buy kind of transaction or a sell kind of transaction. Now things will start becoming more clear. So if I define a DP state, let's say I, J and L. I'm taking L because I have K here. So just to avoid confusion, I'm taking L. I will represent at which particular index I am from 0 to n minus 1. J will represent how many transactions are left, number of transactions left out of K. It can be from 1 to K. It can be actually from 0 to K. Once it is 0, we have to stop the process. And L will be between 0 or 1. If it is 0, then it means that currently I am supposed to do a buy kind of transaction. If it's 1, then it means that I have to do a sell kind of transaction. So this is how I will define my DP table, my DP state, DP of I, J, L. It means at a particular index, how many transactions are left and whether I am going to do a buy or sell. And for this, of course, I'll keep tracking the maximum profit which is possible, max profit. Okay. Now, of course, since we are following a top-down DP approach, where will we start from? So the root node, so to speak, in our recurrence tree will have K number of transactions left. So this N, this I variable of the DP call, the recurrence call, will start with 0. We are at the 0th index. How many transactions are left? This will be K. Okay. And what is L? L is basically the state. And it has to be 0 for the root node, for the starting of the recurrence call. Because, why it has to be 0? Because we cannot have a sell first. We have to do a buy transaction before doing a sell. So we have to initialize our recurrence call with a 0. Now, by the way, just note that when I say we'll be using top-down DP, of course, we have to use DP with memoization. So we'll start a recurrence call using the highest value we have. That is, we are at the starting of the array. We have all K transactions left. We will do a buy transaction first. And we'll keep on breaking the problem. And we'll keep memorizing the values at each state. It's basically DP with memoization. Because if you don't memorize, then we have to keep on doing the repetitive recurrence calls, which will just blow up our time complexity. That is, of course, not the recommended approach. So we have to do DP with memoization. Just a quick note, with memoization. That's why we are defining this array, right? We will store the states. So for a particular state, whatever value we get, we'll store it in this array so that we don't have to do repetitive recursive calls. We'll see it in more clarity when I go through the code. Coming back to the approach. So we'll start from here. This is the original state. Now, what will happen? Since it is 0, either I can do, like I have to do a buy. Now, either I do a buy at index number 0. If I do a buy at index number 0, my current profit will look like minus of prices of 0. I mean, I am buying something, so I'll spend. So net profit will be negative. Plus, on top of it, I'll make a recursive call. Let's call this function something like get profit, get P, get profit, something like this. So this is the initial call that we will do. And then what will happen if I do a buy at 0? I'll get a negative, I'll incur something negative because I'm spending something. And I will make a call to get profit for index number 1 because I have already taken care of index number 0 now. So from index number 1, you still have K number of transactions left because we are doing a buy. Remember that K will reduce only when we do a sell, because a transaction means both buy and sell. So when we are doing a single buy, K will not get altered. So this will still remain K, but this 0 will become 1, indicating that the next thing is a sell because we have done a buy here. So you do a sell. So get profit of 1, that is, start looking from the first index. You still have K transactions remaining, but the state is sell. So here, whatever profit we will get, it will obviously be added to this. We did a buy and then we go through the next recurrence call, and whatever we get, we'll add, which will be the value for this particular state. But is that all? Is that all we can do? No. There is another possibility. What if I say I don't want to buy at 0? In that case, I can simply do a get profit from, I don't want to buy at 0, so I'll start looking from index number 1. Still k transactions are remaining, but the state will still be 0. That is, I have not done a buy transaction. In other words, when I'm looking at, I will represent DP states as white now for clarity purpose. That is the final recurrence relations. So when I'm looking at DP of 0, k and 0, starting from the first index with k transactions with a buy, this answer will be max of these two choices. Apologies for that. Let me clear that down. Yeah. So it will be max between these two choices, this or this. That is, either you did a buy at 0, then you made a recursive call from 1 with k transactions remaining with sell state, or you didn't do a transaction at 0. That is, you didn't do a buy at 0. You just made a recursive call from the first index with buy state. These are the two possibilities. We'll take the max of it. And that will be stored in this particular position, in this particular location of the DP array. And that's how we will keep on breaking the problem down. Just I'll go one step further because I have shown you how a buy kind of recursive call will work. So if it is a sell kind of recursive call, what will I do? Either I will sell at index number 1. If I do a sell, I'll get prices of 1. Remember, since I am buying, I am incurring a negative cost. Here I am doing a sell, so I'll get this as positive. And if I am doing a sell, I'll make the next recursive call from index number 2. Since sell has been done, transaction has reduced, so k minus 1 transactions left, and state becomes 0. I'll go through it once again. Since it is a 1 kind of recursive call, the state is 1, that is sell. So if I sell at index number 1, this is positive cost I am incurring. Along with that, the next call will be from index number 2 with k minus 1 transactions remaining because I did a sell, and the state will become 0 because I did a sell. Sell is 1. So now the current state will become 0. That is, next thing that I can do is buy. K minus 1 transactions are left because a buy and a sell have been done. Starting from here, this is the buy, this is the sell. This is like tracing the path in the recurrence tree. That's what I'm doing. Either this I can do, or I don't want to sell at index number 1, in which case simply I'll just do get profit from index number 2 with k transactions remaining, and the state is still 1. So you change a state when you utilize that index. So here state was 0. It's a buy option. I utilize the index, and then the next option is sell. If you again do a sell at that particular index, you change it to 0 and you reduce a transaction count also. Or you can just push the indices ahead and not do anything. That's as per you. And the state remains as it is. So this is the top-down approach that we are going to use to solve this particular problem. This is the entire idea. Either you buy or you don't buy, depending on the state. And for each call for buy, you have two cases. Either you do buy at that index and change the state, or you move the index ahead. Similarly for sell, either you do a sell at that given index, change the state, or you just move the index ahead. And the base cases for this problem will be something like when k becomes 0, we'll have to stop, or something like, if the number of, let's say if the given index that you are at, so I, this is greater than or equal to n, Will it be greater than or equal to n? Yes. So the start index. So we are starting from 0, right? So if it is greater than or equal to n, then also we stop. So this can be the base cases for us to break out of this top-down recurrence solution. Let's look at the code once to get some more clarity. So this is the code. So here I am defining n as prices.size, the total number of stocks that we have. I am defining sell as k. Sell I am taking as k because, effectively sell represents a transaction. Until unless a sell is done, we cannot say a transaction has been done. So sell is k. I have initialized the DP array exactly the same way I defined the DP array here with 3 states, and initializing the maximum answer as 0 because in the worst case we'll not do any transaction, so the profit will be 0. And I'm starting to do the recursive call from here, which is 0k0, the first 3 states, as discussed in the problem. That is, this is the root call, 0k0. Going to the recurrence function that we have, this is exactly the same as discussed. If we have the start index, the first index, which is more than or equal to prices.size, which is n, that is a break condition, which is this. Or we have sell as 0, that is, the k value, the total transactions remaining, that becomes 0, that is also a break condition. In that case, we just return the value that we have got. Or what we can do is, if we have already memorized the given state, so int min represents that we have not seen a state. But if it is not int min, it means that we have seen that particular state. If we have seen a particular state, we'll just return it, right? Why do we have to do recursive calls? So that's what I was mentioning when I was saying it's DP with memoization. We'll memorize the value we are getting for each particular state, each particular I, j, and l. Because if we don't, then we are wasting our resources. We are doing multiple calls, that is costing us time, that is costing us space as well, because recurrence calls work on heaps. So that is costing us memory as well. So instead of that, let's just memorize if we have seen it, and if we have, then return it. Otherwise, we have two options. Either our state is 0, which is a buy. If it is a buy, then either you do the buy at the given index and push the index ahead and change the state. Sell will not be changed because it's a buy kind of transaction. Or the second option is you don't do a buy there, you just push the index ahead without changing the state, and that's another option. Similarly, if state is 1, that is, we want to do a sell, either you do a sell at the given index, which is positively the value will be added, then you push the index ahead, you reduce the sell count, that is, the transaction has happened, that's why, and you change the state to 0, that is, the next thing we will do is a buy, that is one option. Or you just push the index ahead without changing the sell count, since you didn't do anything at the given index, and keeping the state as 1, that is, you still want to do a sell. So that is the second option. And of course, you have to take max of 2 options and keep on updating, keep on returning the value that you get at each recursive call. That's all that you have to do for this particular solution. Going through the time and space complexity. The type complexity, so space complexity is easy to see because you have a 3D array. This size is n, this size is k, this is 2. So we are by default defining a vector, an array of size 2kn. So space complexity is big O of 2 times k multiplied with n. And if you look at it, time complexity, at most how many recursive calls that you will get? It will be at most the total number of states that you have, right? It's as simple as that. At most how many times recursive calls will happen? It will be the maximum number of states that you have. That's it. Otherwise, we'll encounter these conditions, these base cases, and we'll break out of the recursive tree. So again, this is also big O of 2 times of k into n, just a multiplication of all states. So that's how important defining a state of a DP problem is. If you are able to define the state correctly, what a particular index is, what the next one is, what the next one is, what they are doing, how they are related, what they signify, the problem becomes fairly simple. So that's all for this particular problem. This was the 4th version. So if anyone remembers, we started with the first version. First version was a single transaction, easy problem. A greedy approach is enough. In the second problem, we have multiple transactions. Again, greedy approach is enough. In the third problem, we had two transactions. There we had to use bottom-up maybe with binary states. We started building from below. Like we started defining base cases and then building on top of it. And here we have k transactions. So we start breaking it from top. This is top-down deep. We start from k, we make a recursive call here. And at each step, we keep on breaking it. And we return the most optimal solution. That is, of course, the solution at 0k0 is our solution. That is the starting state. Whatever is returned there is our answer. That's all for this particular video. I would highly recommend again to watch all the 4 solutions in detail. This is a very famous question asked a lot of times in interviews. I have personally been asked these questions for 3 different companies. Yes, 3 companies. So I would strongly recommend to go through the solutions. Once again, thanks for watching the video. See you next time. Bye.